The title of this lesson is Real and Complex Zeros of Polynomial Functions. Now we've talked about real and complex zeros of polynomial functions in the past in the section called Higher Order Polynomials and Their Graphs, where we learned how to graph higher order polynomials using their end behavior and x-intercepts. But all of those in the section that we covered in the past were easy to factor using factoring methods that we've learned in previous classes. Then we took a little bit of time to talk about synthetic division, remainder theorem, and factor theorem. And what synthetic division taught us how to do was to take very large polynomials and divide them by a linear binomial so that we could use the factor theorem to factor the polynomial when it was a very hard thing to factor. And that's what we're going to be putting together today, those two sections. We will be graphing polynomial functions and finding their zeros, but we're going to be doing it where it's hard to factor. To begin the lesson, we're going to be looking at some theorems and definitions before we get into the solving and graphing. The first theorem we would like to look at is the fundamental theorem of algebra, which says every polynomial function of degree 1 or more has at least one complex zero. Now, don't forget that complex is in the form a plus bi, but it could just be the real part, a, or it could be just the imaginary part, the bi, or it could be both of them together. So every polynomial function of degree 1 has at least one zero or root. Next, let's remind us of the definition of zeros of a polynomial. A polynomial function of degree n has exactly n linear factors. For example, f of x equals x plus 5 has a degree of 1. That means that this function will have one complex zero. Complex meaning real or imaginary, or real and imaginary put together. So on the next example, f of x equals 2x squared plus 7x minus 5. Notice here the degree is 2. Therefore, I will have two zeros. On f of x equals 13x to the 5th plus the remaining terms, the degree is 5. Therefore, I will have 5 zeros, including real and complex. And on the last one, again, my degree is 2, meaning I'll have 2 zeros. Although let's take a look at this one a little more closely. I can solve this really quickly. X squared means x times x equals 0, which tells me that either x is equal to 0 or x is equal to 0. Now in this case, the numbers happen to be the same, and so that would be called 0 multiplicity of 2 would be the roots of that equation, or the zeros. So notice, even though it only has one unique zero, including the multiplicity, it has 2, which is the degree that we were looking for. So it even does work with multiplicity. Next, let's talk about the linear factors of a polynomial. A polynomial function of degree n, as long as it's greater than or equal to 1, can be expanded as a product of n linear factors. For example, you could take any polynomial and factor it into a times a linear term times another linear term times dot 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 times as many linear terms as you need. In this case, it would be n linear terms, because in this case my leading term would be ax to the n. So there's n degree, so there'll be n linear factors. Let's just show you how this works. If I have f of x equals x squared minus 25, I can factor that into x plus 5, x minus 5. And I have now factored this polynomial with degree 2 into two linear factors. Now that was a really easy example. Let's try a little bit harder example. F of x equals x squared plus 4. Now, the first example was a difference of squares, which we have a formula for factoring, difference of two squares. Although this next example is the sum of two squares, and we know that that can't factor using our regular methods. So if it can't factor using our regular methods, and I do know that it has zeros because the fundamental theorem of algebra says it has to have zeros, as including the complex ones, let's find out what those zeros are by setting the polynomial equal to 0. I can use the square root method by subtracting 4 to both sides. Taking the square root of both sides, I get x is equal to plus or minus 2i. So it indeed does have zeros. Our zeros are plus or minus 2i, and that's 2 zeros, which would make sense that it has 2 zeros because the degree is 2. So if the degree is 2, then I have to have 2 complex zeros, and I do. So the question here is, can I factor these? If I have the 0, can you find the factor? Well, sure, the factor theorem tells me that I can do that, so I can actually rewrite this as x minus 2i times x plus 2i. So can a sum of squares factor? Well, now you can see that it does factor, so I'm actually going to cross this out, that this cannot factor. In previous classes you thought it couldn't factor because it couldn't factor with real coefficients. But now that we're using complex coefficients, it technically can factor into linear factors, although in previous classes we weren't allowed to use complex coefficients. So it truly does work even for things that don't seem to be able to factor. Next, I'd like to look at the conjugate zeros theorem, which says if f is a polynomial function and a plus bi is a zero of f, then a minus bi is also a zero of f. Now, these two terms, a plus bi and a minus bi, have a special name for the relationship between them, and that special name is called complex conjugates. Complex because we have an imaginary in the term. Also conjugates because the first term is the same, the last term is the same, although the sign in between them are opposites, which makes them complex conjugates, which we've used in previous classes before. But it's important to know that that's their name because I'll be using it verbally a little bit later. It's important to also note that if you have one complex root, that its conjugate will also then be a 0. You can't only have one complex number, they come in pairs. For example, let's take a look at the next problem. It says here, find the zeros. Looking at the factor x plus 3, I can tell you that I have a 0 at negative 3. Setting this next factor equal to 0, I'm getting a 0 at 1/2. Setting the next equal to 0, I'm getting negative square root of 2, positive square root of 2. And these last two are really the ones that I wanted to take a look at right here. If I set these equal to 0 and I move the minus 4 plus 5i to the other side, I'm getting positive 4 minus 5i. Again, if I do the same thing and move the minus 4 minus 5i to the right hand side, I'm getting 4 plus 5i. Notice that these two are complex conjugates. If you have one of these as a root or a 0, then the other one is a must. You must have both of the complex conjugates if you have one of them. Another thing to note here is that the square root of 2 and the negative square root of 2 are also conjugates, but they're radical conjugates. And it's interesting to note that these also come in pairs. So complex conjugates come in pairs as zeros, as well as radical conjugates come in pairs as zeros. So let's use this information to find a polynomial function given some information about the function. On the next problem, we're trying to find a polynomial function. That means I have to start with f of x because it's a function, so I start with f of x. A lot of students will just give me the polynomial, and I'll take off points for that because that didn't give me a function. Of a degree 3, degree 3 tells me I'm going to have 3 linear factors. And I also know that I have zeros of 1 and 5i. Well, if I have 3 linear factors, I also have 3 zeros. I need to know what the 3 zeros are. But they didn't give me all 3 zeros, did they? They gave me 1 0 as a 1 and another 0 as a 5i. And that third 0, well, I don't have it. I don't have that information. But technically I do. Because 5i includes an imaginary number, it is a complex number, so it has a conjugate 0. Because I have a 5i, I also have to have its complex conjugate, negative 5i. This right here is an implied 0. You cannot have a 5i without having its conjugate, negative 5i. Now that I have the 3 zeros, let's put them together and find a polynomial function with degree 3 with the following zeros. So f of x is equal to, if I have a 0 of 1, my factor is x minus 1. If I have a 0 at 5i, then my factor is x minus 5i. And if I have a 0 of negative 5i, then my factor is x plus 5i. And this is my polynomial function. Instead of multiplying it out, I'm going to ask you to just leave your answer in factored form. For the next problem, we are asked to find a polynomial function of degree 6. Degree 6 means I have to have 6 zeros, 6 linear factors. So let's look at the information given. I have zeros of negative 2, that's 1. Also negative 1/2, that's my second 0. 3 plus 2i, that's my third 0. And 4 minus root 5, that's my fourth 0. And how many zeros am I expecting? Well, 6 zeros. So I'm missing 2 of them. Where am I going to get the next 2? Well, looking at 3 plus 2i, I know that's a complex number. Because the complex numbers come in pairs, I know that I have an implied 3 minus 2i, 0. That will be my fifth 0. Because complex numbers come in pairs of their conjugates. Similarly, radicals will also come in conjugates, so because I have a root 5, I'll know that has an implied 0 as well that comes with it, and the implied 0 there is the radical conjugate, or 4 plus root 5. And that's my sixth 0. So this is a tricky problem because it only gave you 4 zeros, but it told you that there were 6 here. You had to find the other 2 knowing that they were implied. Let's go ahead and find that polynomial function. Again, functions start with f of x. If my first 0 is negative 2, then my factor is x plus 2. My second factor is negative 1/2. I could either write x plus 1/2 or 2x plus 1 for that particular factor. Remember, it says find a polynomial function. It doesn't say find the only polynomial function. There could be many answers to this problem, which would still get you the correct polynomial function with this degree with these zeros. So there's more than one answer for this particular problem. The next one, if I have 3 plus 2i, then my factor will be x minus 3 minus 2i. Let's go ahead and do his conjugate right with them. 3 minus 2i is the 0, then x minus 3 plus 2i would be its factor. 4 minus root 5, if that is my 0, then my factor is x minus 4 plus the root 5. And then the last one, 4 plus root 5, my factor for that 0 would be x minus 4 minus the square root of 5. Again, don't bother multiplying this all out. You do not need to do that. Just leave your answer like this. One more thing I'd like you to remember here is when you're taking the opposite sign of the 0 to put it in the factor, if there's more than one term in your 0, like 3 plus 2i, you take the opposite of both the 3 and the opposite of the 2i. You change both of the signs. Notice here when I took the 3 minus 2i, I took the opposite of 3 and the opposite of negative 2i all the way down the line. So that covers the theorems that we needed to discuss. Now we're actually going to be using the theorems.